Download this code from codegive.com, link in the description below. OK, let's dive into the fascinating world of parsing ambiguous sentences using probabilistic parsing, with a code example in Python. This will be a comprehensive tutorial covering the concepts, implementation, and nuances. Module 01, Lecture 39, Parsing Ambiguous Sentences, Probabilistic Parsing. The problem, ambiguity in natural language. Natural language is rife with ambiguity. Sentences often have multiple possible interpretations, stemming from various sources. Lexical ambiguity. A word can have multiple meanings. For example, bank can refer to a financial institution or the side of a river. Syntactic ambiguity. The grammatical structure of a sentence can be interpreted in multiple ways. This is the main focus of this lecture. Semantic ambiguity. Even with a fixed syntax, the meaning can be unclear. Referential ambiguity. Uncertainty about what a pronoun or noun phrase refers to. Consider the classic example. I saw the man on the hill with a telescope. This sentence is syntactically ambiguous. Here are a few possible interpretations. 1. I used a telescope to see the man on the hill. The telescope modifies saw. 2. I saw the man who was on the hill and possessed a telescope. The telescope modifies man. 3. I saw the man on the hill while I myself possessed a telescope. The telescope modifies I. Traditional parsing techniques, example context-free grammars without probabilities, would likely produce all possible parse trees for such a sentence, without any indication of which tree is the most likely or most plausible. This is where probabilistic parsing comes in. 2. Probabilistic context-free grammars, PCFGs. A PCFG extends the standard context-free grammar, CFG, by assigning probabilities to each production rule. Formally, a PCFG is a tuple. N*, a finite set of non-terminal symbols, example S, NP, VP, PP. Sigma*, a finite set of terminal symbols, words. R*, a finite set of production rules of the form A-alpha, where A set membership symbol N and alpha is a sequence of symbols from N union set symbol sigma, star. P*, a probability function that assigns a probability P, A-alpha, to each rule A-alpha, such that 0 less than or equal to P, A-alpha, less than or equal to 1, probabilities are between 0 and 1. Sigma P, A-alpha, equals 1 for all A set membership symbol N, the probabilities of all rules expanding a non-terminal must sum to 1. A-alpha set membership symbol R. Example PCFG*. 3. The probability of a parse tree. The probability of a parse tree is the product of the probabilities of all the rules used in that tree's derivation. For instance, consider this parse tree for I saw the man on the hill. Note, we'll simplify and assume I is a proper noun and therefore NP-I directly. The probability of this simplified tree would be 1.0 S-NPVP, asterisk 1.0, NP-I, asterisk 1.0, VP-VNP, asterisk 1.0, V-SAW, asterisk 0.6, NP-det-N, asterisk 0.5, det-the, asterisk 0.8, N-man, equals 0.24. Why probabilities help? Probabilities provide a way to rank the different possible parse trees for an ambiguous sentence. The tree with the highest probability is considered the most likely interpretation. This allows us to resolve ambiguity in a statistically grounded way. 4. Probabilistic parsing algorithms. Several algorithms can be used for probabilistic parsing. The most prominent are 1. Viterbi algorithm. For CKY parsing, the Viterbi algorithm is a dynamic programming algorithm used to find the most probable parse tree for a given sentence according to a PCFG, specifically when using the Chomsky normal form, CNF, transformation. More on this below. 2. Early parsing. Probabilistic, a more general parsing algorithm that can handle a wider range of grammars, not just CNF, and can be extended to probabilistic parsing. 3. Maximum entropy parsing *, a discriminative approach that learns the probabilities of parse trees directly from data, rather than estimating them from individual rule probabilities. V. Chomsky normal form, CNF. The Viterbi algorithm, in the context of PCFGs, typically requires the grammar to be in Chomsky normal form, CNF. A CFG is in CNF if all production rules are in one of the following forms. *A-BC, a non-terminal produces two non-terminals. *A-A, a non-terminal produces a terminal. Any CFG can be converted to CNF. The conversion involves the following steps. 1. Eliminate null productions, epsilon remove productions that produce the empty string. 2. Eliminate unit productions, B remove productions where a non-terminal produces only one other non-terminal. 3. Introduce intermediate non-terminals * replace productions like A-BCD with A-BX, X-CD, where X is a new non-terminal. 4. Separate terminals * replace productions like A-BC with A-BX, X-C, where X is a new non-terminal. Example: CNF transformation *. Original grammar. CNF equivalent. 6. Viterbi algorithm with CKY parsing for PCFGs, detailed explanation. The Viterbi algorithm, combined with the Koch-Kazumi-Younger, CKY, parsing algorithm, is a standard approach for finding the most probable parse tree given a PCFG in CNF. Here's a breakdown. A. CKY parsing, bottom-up dynamic programming. CKY parsing is a bottom-up chart parsing algorithm that systematically builds a parse table, or chart, for a given sentence. The table represents all possible constituents that can be formed from the sentence. Input *, a sentence W equals W1 W2, Wn of length n, and a PCFG in CNF. Table *, an nxn table called chart, where chart I, j contains a set of non-terminals that can derive the substring Wi plus 1, Wj. B. Algorithm steps *. 1. Initialization * fill in the diagonal of the chart. For each word Wi in the sentence, add all non-terminals A to chart I1, I such that there is a rule A-Wi in the grammar. Store the probability P, A-Wi, along with the non-terminal A. 2. Iteration *, iterate over all possible lengths len from 2 to n. For each length len, iterate over all possible start positions I from 0 to n, len. The end position j is then I plus len. For each I and j, iterate over all possible split points k between I plus 1 and j. For each non-terminal b in chart I, k and each non-terminal c in chart k, j, check if there is a rule A-BC in the grammar. If there is such a rule, add A to chart I, j. The probability of A deriving the substring Wi plus 1, Wj is the product of the probability of the rule A-BC. The probability of B deriving Wi plus 1, Wk. Asterisk the probability of C deriving WK plus 1, WJ. If A is already in chart I, J, keep the A with the highest probability. This is where the Viterbi algorithm's dynamic programming comes into play. We only keep the best probability for each non-terminal at each cell. 3. Termination asterisk after filling the entire chart, check if the start symbol S is in chart 0, N. If it is, the sentence is parsable according to the grammar. The probability associated with S in chart 0, N is the probability of the most probable parse tree. See backpointers, for recovering the parse tree. To reconstruct the actual parse tree, not just the probability, you need to store backpointers along with the probabilities in the chart. When you add a non-terminal A to chart I, J because of the rule A-BC and the non-terminals B and C in chart I, K and chart K, J respectively, store pointers from A to B and C as well as the split point K. After the chart is complete, you can trace back from S in chart 0, and to reconstruct the most probable parse tree. 7. Python code example, Viterbi with CKY. 8. Explanation of the code. 1 PCFG class asterisk. Asterisk underscore underscore init underscore underscore, initializes the PCFG from a dictionary of rules and probabilities. The keys of the dictionary are strings representing the rules, example S-NPVP, and the values are the probabilities, as floats. It stores the grammar in a dictionary where keys are the left-hand side, LHS, non-terminals, and the values are lists of tuples, where each tuple contains the right-hand side, RHS, symbols, as a list of strings, and the corresponding probability. 2 Viterbi underscore CKY function asterisk. Asterisk initialization asterisk creates the chart and backpointers dictionaries. The chart stores probabilities of non-terminals deriving substrings, and backpointers stores the information needed to reconstruct the parse tree. Asterisk terminal rule initialization asterisk fills in the diagonal of the chart for terminal symbols, words in the sentence. Asterisk CKY iteration asterisk iterates over possible lengths of substrings and split points within those substrings. Asterisk rule application asterisk for each possible rule A-BC, it checks if B can derive the left part of the substring and C can derive the right part. Asterisk probability calculation asterisk calculates the probability of the rule being applied and updates the chart and backpointers if a higher probability is found. Asterisk parse tree reconstruction asterisk after the chart is filled, the function checks if the start symbol S is in the top right cell of the chart. If it is, it reconstructs the parse tree using the build_tree function. 3 build_tree function asterisk. Asterisk recursive reconstruction asterisk recursively traverses the backpointers to reconstruct the parse tree. Asterisk terminal case asterisk if a backpointer is none, it means we have reached a terminal symbol, word. 9. Key improvements and considerations. Asterisk log probabilities asterisk to avoid underflow issues, probabilities getting extremely small, it's often better to work with log probabilities. You would take the logarithm of the probabilities and perform addition instead of multiplication. Remember to exponentiate the final result to get the actual probability. Asterisk grammar engineering asterisk the performance of a PCFG parser heavily depends on the quality of the grammar and the accuracy of the probabilities. Manually constructing a good grammar can be time-consuming. Methods for learning PCFGs from tree banks, annotated corpora of parse trees, are commonly used. Asterisk smoothing techniques asterisk when learning probabilities from data, you'll encounter rules that are never observed. Smoothing techniques, example add-one smoothing, good Turing smoothing, can be used to assign non-zero probabilities to these unseen rules. Asterisk dealing with unknown words. Asterisk handle unknown words, words not in the grammar's vocabulary, by assigning them to a special UNC category or by using techniques like morphological analysis to guess their part of speech. Asterisk larger grammars. Asterisk for more complex grammars, consider using optimized data structures and algorithms to improve parsing efficiency. Asterisk real-world parsers. Asterisk libraries like NLTK and Spacy provide pre-trained probabilistic parsers that are more sophisticated and efficient than the simple example provided here. These libraries often use advanced techniques like lexicalized PCFGs and discriminative parsing models. Asterisk lexicalized PCFGs. Asterisk extend PCFGs by incorporating lexical information into the rules. For example, instead of just having a rule VP-VNP, you might have rules like VP, SAW-V, SAW, NP. This helps to capture dependencies between words and improve parsing accuracy. Asterisk evaluation. Asterisk to evaluate the performance of a probabilistic parser, you can use metrics like precision, recall, and F1 score, comparing the parser's output to a gold standard tree bank. Going further, practical applications. Probabilistic parsing is a core technology in many natural language processing applications. Asterisk machine translation. Asterisk parsing sentences in the source language and generating grammatically correct and semantically equivalent sentences in the target language. Asterisk information extraction. Asterisk identifying and extracting structured information from unstructured text. Asterisk question answering. Asterisk parsing questions and text to understand the meaning and find relevant answers. Asterisk sentiment analysis. Asterisk parsing sentences to understand the sentiment expressed. Asterisk dialogue systems. Asterisk parsing user input and generating appropriate responses. By mastering the concepts and techniques discussed in this lecture, you'll be well equipped to tackle the challenges of parsing ambiguous sentences and building more robust and intelligent NLP systems. Remember that practical experimentation and working with real-world data are essential for truly understanding the nuances of probabilistic parsing. Good luck.